Good morning all of you. Today we are going to discuss about approximation solutions of Navier-Stokes equations. That is what we earlier you started to how to approximate the Navier-Stokes equation for simple problems flow through two plates with movable plate with pressure gradient. Same way we can look it for solutions of Navier-Stokes equations for pipe flow through a concentrated circles. We can do that, but today we will solve two problems, mathematical problems. Then we will discuss about the boundary layer approximations for Navier-Stokes equations. That is what today very detailed I will talk about boundary layer approximations, how we do it for boundary layer problems. So, that is the problems what I will introduce to you. Here I can look at the mostly we are following Sinzel Simbala books as well as FM White for this part of the lectures. Basically what I will talk about this most of the books I will come back to that. So, we will talk about how we do this boundary layer approach equations and also boundary layer approximations. Before that again we have to solve two problems. Maybe next class we will talk about different thickness like displacement thickness, momentum thickness and also the turbulent plate boundary layers. That is what we will discuss it later on part. Let me I go to solve very simple problems. The problem is that there is a steady, again I am emphasizing, two dimensional incompressible velocity field is given to us. We have to compute a function's pressure is a function of x and y. Okay. So, if you look at that the velocity field what is given to us, which is having the scalar component in x directions, x b, this is u functions and you have minus a y plus c x j functions. Okay. So, this is the u component, this is the v component. Okay. So, this is what we have the functions of u b, the scalar components. You have to check first what are the assumptions are there. If you look at that both the u and b does not have any time component. So, it is a steady flow, you just to have to verify it. So, it is a steady flow as the u and v scalar component does not have a time dependency. So, it is a steady flow and u and v does not have a functions of z. So, the flow is two dimensional. So, this understanding you should have. So, as u and v does not have any dependency function in the z directions. So, we have the two dimensional flow and this rho is a constant as it has given for us the density is a constant for incompressible flow. So, these things are given to us. Now, we are looking at whether what is the pressure field we have to compute it, which will be a function of as a two dimensional flow, steady two dimensional incompressible flow. So, we will have a functions of x and y which is there. With us what is there, because two dimensional incompressible flow we have a continuity equations, we have continuity equations for two dimensional flow, you know it del u by del x plus del v by del y, that should be equal to 0. That is then we have the Navier-Stokes equations in two directions x and y direction. Z I would not need it because it is a two dimensional flow field, two dimensional flow field. So, with us we have a continuity equations, we have a Navier-Stokes equations which are linear momentum equations in x and y directions. That these are three equations we will put it to past. So, continuity equations will use it to confirm that whether these equations the velocity field what is given it functions of x and y, do they satisfied or not. That is what is that flow is steady, incompressible and two dimensional in x, and the gravity does not act in either in x and y directions. So, another assumptions we have put it, so that to neglecting this the gravity components. Okay. That is the assumptions if you can look it. Now, if you look it first to check it, does this velocity field satisfy the continuity equations. If you satisfy, then this is the basic velocity field for which we can derive the pressure field. If the velocity field does not satisfy the continuity equation, we should not find out the pressure field for that. So, as the fluid we have a continuity equation, so we have Navier-Stokes equation, we are looking at doing the continuity equations, we are looking at which is incompressible continuity equations, we are using it to satisfy whether the velocity field what is given it really for the fluid flow case or not. So, you can do a simple partial derivative of u field del u by del x. If you look at it, it is a del u del v by del y, it will be minus a. That is by just inspections you can locate that what is coming it. So, this way you can always find out through just looking these components, that del u by del x is a and del u by del v small v by del y is minus a. So, combinations of these is 0, that is what it satisfies. That means, the velocity field whatever is given it, that is it is satisfying the continuity equation. So, we can determine the pressure field, that is what we can define the pressure field. If continuity equations are not satisfied, we could stop here, because it is not a given field, could not be a physically possible. So, okay, that is try to understand it. So, what I want to emphasize that you look at this is not mathematics problems, it is the problems of fluid flow. So, first foremost requirement for us to get the pressure field, the continuity equation should be satisfied. If not, then you need not to compute the pressure field, because it does not represent the flow equations, that is that flow field. So, that is the idea, you should understand it. The same way if you look at I am just go for the pressure field calculations. As I said it, we have a two momentum equations, we have dropped the gravity components. Again I can write it two dimensional, even if it is here two dimensional Navier-Stokes equations. Let me I write for in the x directions. Okay, that is what you can have a practice. Okay. We remember it is a steady. So, we do not have a local accelerations component, it is a steady flow. So, there is and it is a two dimensional. So, z components is not there, that means w is a 0. So, anything by del z or del square by del z square all are 0. So, that is very basic things you should know it as soon as it is a two dimensional things. That is what will be help us to write Navier-Stokes equations in a simple form. So, we have only convective accelerations in two directions. So, first x directions I am writing it. So, this is v del u by del y that is a convective accelerations part, rho g x minus grade p by grade x plus mu times of Laplace operators, that is what we are expanding here. That is what you have to have a trick to how to expand Navier-Stokes equations. You can expand it, look at the local accelerations term. Okay. There is a gravity force component, the pressure force component and viscous force. This is 0. Anyway, we made it. There is no component of g x. So, what I have? I have the second derivative of second partial derivative of v u with respect to x and y, all will be the 0. So, just looking the functions. Okay. So, only I have these two terms. I have only these two terms. So, as I have the two terms, if I just rearrange it, I will get it del p by del x is equal to rho times of, this is what coming from the convective acceleration terms. As you do the partial derivatives multiplied with v, partial derivatives with respect to y multiplied with v, we will get it a square x minus a v. Same way, if you apply the momentum equations in the y directions, I will get this component. So, just same way I will get the component. This component anyway 0 and this component is 0. So, again you will get it a partial derivative of pressure field with respect to x directions. We have a functions, we have a. So, from this we have to derive p x y. So, the basically we are looking at what is a function of p x y, the pressure field, that is what you are looking at. So, here we do a very simple calculations, we do it with the integrations, finding out the integration constants, substitution methods, what we in generally do in mathematics subject. As you know the partial derivative of pressures of in x direction, y direction, how to estimate the pressure p x y, this is a simple integrations and putting this concept. For examples, first you can just find out the pressure field should not be a smooth functions, should not have any sudden discontinuity. That is one means either of the p or derivative of p, they do not have to any discontinuity functions. That is what you can looking the inspections you can find out. Now, if you look at that requires to you can differentiate it, also you can cross differentiate it, like to know it whether this cross differentiate, that is what is giving a conditions for the smooth functions. Okay. Is equal to, if it is equal to the del x by del x del phi by del y. Okay. If this is satisfied, that means function is a smooth functions, there is no sudden discontinuity. Okay. This is a partly it is mathematics part, but please when you go for a partial differential equation form of Navier-Stokes equations, looking for exact solutions, always you will have look at the mathematics part more as compared to the fluid mechanics. Okay. That's the difference, but I do believe it that that's what you have to look at if you are looking at function p x y. So, as you have to look at whether there should not be sudden discontinuity. So, you have to change the order of differentials and then cross differentiate it. If they are satisfying, that means velocity satisfy the steady two dimensional incompressible Navier-Stokes equations. Now, I need to compute the pressure field, which is again I will get that is all the mathematical steps used to get it the functions. So, as I know the d phi by dy as a functions. So, if I integrate it, I will get the p x y functions. If I just integrated that, I will get a p y functions with a function of the constant can be defined as a g s. Okay. So, that g s you can just do a partial derivative of these functions, then you can get it these functions this way, and if you substitute g x value finally you are getting a functions looks like a having second order term x square y square, x and y, and a, b, c are the constants, and you have a additional c1 constant. So, if you look at we simple, if a velocity field is given it to estimate the pressure field, we have to go analytically derive the pressure field using these two equations with us. The continuity, again I am just revising you to that, and Navier-Stokes equations. This is two equations, three equations we are using for this is one. This for the two dimensional case we have a three equations we are using it for a given velocity field, we can get a pressure functions. But be remember it, it's not like mathematics that we are using it, we are satisfying the conditions like whether the p x y is a smooth functions or not. We are satisfying with the continuity equations to know it whether it is a velocity field, what is given it. Does it satisfy the continuity equations? If it does not satisfy the continuity equations, you need not to estimate the pressure field, because this is not representing the flow field. There is no meaning if the velocity is not representing the flow field in a continuity equations, then we need not to go for estimating the pressure field. That's the difference between a mathematicians and the fluid experts, which look at that first the continuity equation satisfaction should be there, then followed by we look at the Navier-Stokes equations to determine the pressure field. So, that is the very easy problems what I have solved it, but solve it, but you try to look at how complex functions can be given it to determine the pressure field. Now, second problems, just to demonstrate it, we do not require only the velocity field and pressure field. Many of the times we need to know it, what is wall shear stress, what is stream functions for a particular flow field, verticity, velocity potential, and average velocity. So, we are taking the same problems, that there is a fixed plate, okay. The flow is going because of the pressure gradient, because of del p by del x, this is the pressure gradient, and we have a x, okay. These are two plates are there, which we in the last class we solved it, pressure gradient is there, and you have the velocity v, and you have a y, this is minus h, this is plus h. So, this is the field what we used to solve it. We have already solved this part. Today, we are looking at what will be the wall shear stress at this point, also at this point, stream function, verticity, velocity potential, and the average velocity if known the velocity field. So, the last class we estimate this velocity field from Navier-Stokes equations that we assume it v w is a 0, okay, neglecting the gravity force components. We get this u component, that is what we did it last class, minus dp by dx, okay, that is what dp by dx is equal to a square by 2 mu types of 1 minus y square by h square. This is the velocity field, we got it applying this Navier-Stokes equations. As you remember it, this is what the velocity field we got it for the pressure gradient, which would have a function of h mu dynamic specificity 1 by h square, the paraboloid shape, okay. This is will be the shape will come like this, shape will come like this as we have a two fixed parallel plate. So, now it is easy. So, you have to know the first velocity field, okay, and is a function of dp by dx, that means p is varying only x directions. If it is that, we can compute this part now if you look it, I am just substituting wall shear stress using the Newton's laws of viscosity. We can get tau x y wall. Fluid kinematics, we have done this part. Mu is equal to del u by del y, del v by del x at wall y equal to plus minus h. This is what? So, plus h, this is minus h. Okay. So, del v, v is 0, we know it. So, you only have a u functions, that is what the functions we just substitute here, do the partial derivatives, finally we get it this part. Okay. Finally, we get this part. So, the value of the at this point will be the dp by dx into h. Here will be dp by dx equal to minus h. So, that is what will be the shear stress distributions will come it. Okay. This will have a in terms of u max, also we can get it as a 2 mu times of u max in it. So, simple, just substitute it, do a partial derivative with respect to y and get it, which is the basic definitions as we derive from the flow kinematics. Okay. Now, if I look it as the plane, okay, it is a 2-dimensional plane flow, that is what. So, it can have the stream flow. Okay. Stream functions we can get it, because it is a 2-dimensional flow. Okay. As the x and y flow is steady and incompressibles. So, you know it u equal to definitions. Okay. So, just integrate the u, then you will get it the functions u max. So, you will get a functions which you will get it this function, just to integrate it from setting the psi equal to 0 at the center line. So, this is what psi equal to 0. So, you can integrate it to finally will get it these functions. So, that is what is showing it. So, you can get a streamline functions. Okay. And that is the value what will be there, the value at this point at the both the walls. Okay. That is plus and minus signal will be there. So, we are getting the stream functions, we are getting the stream function as we are considering the centralized is a stream function is equal to 0. We can setting that value, then we can get it what will be the stream functions value at both the fixed walls. Both the fixed walls we can estimate it what is the stream function. So, if you look it, it is not a difficult, only you have to look at what is the relationship between wall shear stress, which is a xy plane, how similar way, what is the relationship with the velocity and the stream functions. That is what we did it very extensively looking to divide this thing. The same way I look at the verticity. Okay. So, verticity in the jet plane, that is what you have a x and y. So, you are looking at the verticity which is perpendicular to this plane. So, as you will again going back to the fluid kinematics, we are looking for curl v. Okay. So, we are looking at curl v in z directions. So, that is what is d v by dx. I just writing u dui. So, v is 0. So, only you know this partial derivative of the y, which will comes up to this value. Okay. So, a non-linear verticity components are there. So, now if verticity components are there, as we discuss it, we cannot get the velocity potential functions, because to get a velocity potential function, flow should be irrotational. So, that is what is here justified it. You need not to estimate the velocity potential function, because potential function does not exist because flow is not irrotational. So, that is the comprehensive idea of the fluid mechanics. You have to understand it, we have to estimate the vorticity. If vorticity vector could be 0, we could compute the velocity potential functions, but in this case we cannot compute it because flow is not irrotational, the velocity potential functions does not exist it. Then you have to compute the average velocity. It is a very easy that for a if I considering this discharge, which is a u dA velocity in area integrations from minus h to plus h, divide by this area, I will get it integrations over this, we will get it. B is the dimensions is a perpendicular to this plane, that is what is a unit dimension, sometimes we can consider it. This is what the dy, so we will get it the average velocity. So, giving these two examples, just you want to understand it when you apply Navier-Stokes equations to estimate velocity field, or you try to look at the shear stress, wall shear stress, the stream functions, the velocity potential function or the average velocity. So, as we have the functions, we do partial derivative, we do the integrations, differentiation, all these things we apply it to get it from basics relationship. We try to get it what will be the average velocity, what will be wall shear stress, what will be the stream functions, what will be the velocity potential function or the vorticity. So, that it is a give it is a examples here as compared to integral approach where we simplified many things, but in case of the differential approach we need to do the integrations and differentiations to get the pressure field, to get wall shear stress, to get stream functions, velocity potential function with a lot of series of approximations, 2-dimensional flow, incompressible, Newtonian fluid. So, that is what I am repeating it to tell it that fluid flow problems are not easy, you simplified it for a specific cases to get some solutions. Now, let us go for a very interesting topics, which is the boundary layer approximations, or where we do need the Navier-Stokes equation solvers. Like for example, as is given here, again I will be sketch that same figures for your convenience and better understandings, that there are the two chambers are there, and these chambers are connected with a pipe. Okay. The liquid is coming from these chambers and filling is happening in these chambers. This is the pre-pressure press, the tank 1 and tank 2. One is supplying tank, another is filling tank. The same figures I am just drawing it to make a more attention to figures. So, if you look at this way, that we have had two tanks, the liquids are there and the liquid is coming from tank 1 supplying tank to the receiving tank. If it is happening that, see if you look at when fluid flow is coming it, that is what we have to understand it. Fluid flow is coming it, okay, you try to understand is a virtual fluid balls, okay, that balls are coming it, which is are closer to the boundary. At that boundary we will have a no slip boundary conditions. That means there is regions very close to this flow where the flow is coming it, we will have a regions where is a low to maintain the boundary conditions, the no slip boundary conditions, you will have a very thin layers which will be making a viscous as well as you have the layer will have viscous and rotations near to this, because near to the wall as is a no slip boundary condition, velocity has to be 0. So, because of that, the fluid particles which are the nearby, they will also retract it. So, there will be regions will form it very close to this wall, where you will have a viscous dominancy will be there, and there will be velocity gradients, and that is what will act a shear stress on this wall. Exactly same way as the flow is coming it, there will be a formations of regions where be viscous dominancy will be there, the vorticity will be there, and these the regions we call boundary layers. These the regions we call boundary layers, okay, close to the boundary. So, that is the reasons we define it as a boundary layers, is in the regions where you have a vorticity, where you have a viscosity dominancy is there, but this layer is very thin as compared to the flow domains. These are the regions where we have the boundary layers. So, this is very close, very thin, but to just to represent you, I just magnified it. Okay, it is not like this thickness. So, there will be a boundary layer formations will be presenting in that, which is because of presence of these two walls. Okay. As the fluid particles are coming it, not all the fluid particles here will be active for the flow is going through this. There are the fluid will commit a regions very close to this, we will have a flow will commit, flow will go like this, flow will come, flow will go like this, they will have a flow like this. So, in fluid mechanics you have to understand it, how the flow happens at different scales. It is not a simple mathematics, or it is. So, that visualizations, conceptual visualizations is required. That means, the flow at these regions, they will not have any rotational. Okay. These the regions flow will have a irrotational. Okay. And viscosity will not dominate it. So, that is the reasons we can use Euler equations. Okay. So, if you look at, there is a two tanks, it is a simple examples. Okay. But indeed that two tanks, how type of the flows are happening? There are the regions where the boundary layer formations are there, viscosity dominant is there, vorticity is there. There is a regions where there will be no rotational field will be there, all the streams will come like this, which where we can use the Euler equation. But just after these regions, okay, of this flow jet, it will act like a flow jet. In those regions you will have viscosity dominated as well as the vorticity dominance. So, you need to have a Navier-Stokes equations. So, NS equations you need to have. What will happen to this? This will act like fluid at the rest or fluid statics. Same thing is fluid at the rest. So, with this very simple examples, if you can look it with a very simple problems, that we have a two tanks, one is a supply tank, another is a receiving tank. Within that tank flow zones, there are the regions behave like a fluid at the rest, that is what will happen it. These regions will remains like a fluid at the rest, there is no stress component at all. So, only the gravity force and the pressure field, that is what we discussed that. There is a regions where the flow is irrotational regions, where only the streamlines will come like this. There are the regions close to the wall, where they have a boundary layers, there will be large vortices, vorticity will be there, viscous dominancy will be there. Then you have the regions where you need to have a full Navier-Stokes region, that is what is showing it, full Navier-Stokes equations, because there is a jet coming it, as a jet mixing with waters or any liquid. So, there is a jet, the water jet, you just visualize the flow, there is a water jet. So, as the water jet is going it, and this two, so in these regions the viscosity will dominate the all these, you have a vorticities will be there. So, those regions we have to solve with the Navier-Stokes equations. This is the fluid at the rest conditions. So, that means we need these simple cases, we have a 4 type of conditions. Fluid at the rest, which we discussed very beginning it. We also discuss about irrotational flow area, which is Euler equations. We also discuss about the Navier-Stokes equations. We approximate it or we know it from computational fluid dynamics. We can solve these problems. And other one is the boundary layers, very thin layer near to the boundary. You will have the viscosity dominancy as well as the vorticity. How we can approximate that, which will be a form of a solutions of Navier-Stokes equations. That is the things let us discuss with, which is will be lot of approximations, because computational fluid dynamics, as I said it very beginning, is that it has grown last 3 to 4 decades. But how do you solve very challenging fluid mechanics problems in early 90s, because that times in World War II we used to have a spacecrafts. So, without fluid mechanics knowledge, how we develop these aeroplanes, how we develop the best challenging fluid mechanics problem solutions. The balancing between them is that the boundary layer approximations. That is what I will talk about here. That so you will have a lot of problems is comes it, and we need to have a take care of equations for the approximations. Okay. So, equations of approximations we have to look it. It's not like as you can always have a debate it. Today we have a CFD with us. Okay. Computational fluid dynamics tools with us. What is necessary to learn boundary layer approximations? Okay. Boundary layers. But that's what I will justified it with giving some examples that still even if I have a best solver, the computational fluid dynamics solvers are there, still today we should have a understanding of the boundary layers. So, our understanding of the boundary layers with experimental fluid mechanics, okay, experimental fluid mechanics, okay, which we are not covering lot, but just have a demonstrated few of the cases. Really we can solve many challenging problems using knowledge of the boundary layers and knowledge establishing this empirical relationship from experimental fluid mechanics. So, they are complementary each other. That is not that CFD only can solve the problems. CFD plus boundary layer and experimental fluid mechanics, they are complementary actually to understand very complex fluid flow. Okay. So, it's basically talking about any biomechanics and all, where really we have a complex problems. Okay. So, with this note, let's come back to the boundary layer approximations. Basically it is a bridging, it very simple word. It is a bridging between the Euler equations and the Navier-Stokes equations, because Navier-Stokes equations solves with a no slip boundary conditions, but Euler equation does not have a it has to have a slip boundary conditions. Like for example, if I get it, if you just take a simple form of cars. Okay. Okay, this case is not that perfect, but anyway, that does not matter it. It is moving with velocity v. So, let be maybe 100 meter per second. Okay. So, which is if I have the velocity v is I have a car is moving with the velocity v, with our understanding it that you will have a opposite like this, you will have a free stream velocity and car is standing it. Okay. So, free stream velocity will be the v and car is at the rest conditions. That is what just opposite we do it with a relative wind testings. If you do that, you can this is the pre-stream velocity. So, this is the front side of car. So, there will be a boundary layer formations will happen here. There will be a boundary layer formations will happen here. There will be the boundary layer formations will happen here. At the top, you will have the flow will go like this, where the Euler equations are valid. Euler equations is valid. That is not a big issue. Here, the Euler equation is valid, but the boundary in Euler equation is a slip conditions, but reality it is not a slip conditions, it will no slip, and there is a formations of boundary layers. Okay. Formations of boundary layer. These boundary layers will be change the pressure distributions. These boundary layers will be change the velocity close to this surface. This boundary layer is responsible for what will be the drag force will be act, what will be the lift force will be act. So, there will be a combinations of boundary layers and the Euler equation solvers solve this problem, instead of looking for Navier-Stokes equation solver. So, we are just replacing, or we are just that is what is early before I can say 1940s or 50s, almost all the scientists they try to look at an alternative way to solve this Navier-Stokes equation is that near to the boundary you solve these boundary layer equations, just far away from this you apply this Euler equations. The boundary layer approximations always most of the books written in a very complex way. So, lot of mathematics and all, but the conceptually it is a very nice concept, looking at how the approximation has depended very complex flow to get some sort of solutions. Instead of the Navier-Stokes equations, we are looking at boundary layer equations. Okay. That is what today I will be discussing on this. We are looking boundary layer equations. We are not looking which is a part of a Navier-Stokes equations only. That is the flow physics is the same, the mass conservations and linear momentum equation. Some form of this Navier-Stokes equations we are trying to look it as a boundary layer equations. As because when you talk about the drag and lift force of a car, it all depends upon a very thin layers, how it is formatting over the surface. Okay, as the car is moving it, this thin layer is responsible for the shear stress, this thin layer responsible to because the pressure distributions. Combination of these thin layer, which is the boundary layers with the Eulers, if I can solve it with a degree of approximation of Navier-Stokes equations, that what we can solve it, because as you know, as we discussed many times, we do not have analytical solutions of Navier-Stokes equation for all the problems. Very few problem, simplified problems we have. So, now if you look at that is the concept is coming that you need to have a boundary layers, is again I am repeating it is very thin layers, could be a millimeter levels, could be the centimeter levels. Okay, boundary layers thickness are the very small, except okay, I am not talking about atmospheric boundary layers, which is much bigger size, but the automobile boundary layers flow through any flow past an object is a very thin in order of the millimeter or the centimeter order. So, what instead of looking at the cars, the people have considered, let you consider a simple plate, which is very easy. Okay. To simplify the problems, not looking at complexity at the very beginning, looking at consider as a plate, and you have a uniform stream flow. Okay. You have uniform stream flow, many of the times we designate as capital U stream flow. Because of this, there will be a boundary layers formations will be there, which will make it a boundary layer formations will be there like this. Okay. So, if you look at that, this will be symmetry. Okay. So, that is the reasons we always talk about this part as it is a symmetric. Okay. So, we simplify that. When you have a plate, when you have uniform stream flow, definitely there will be boundary layer formations in both the sides of the plates, but symmetry point of view, many of the books show the boundary layer formations from this. Okay. And that is what they consider only symmetric boundary layer formations. That is what is biggest problems. That this is only the symmetric boundary layers I am looking at. At this point, I know this velocity is 0, and I have this x, and this is the x directions, is L is a length of the plate. This is what my boundary layer thickness, which is a sigma x, which varies with, is a thickness. How do we define it? We define the boundary layer thickness if this u is the velocity, 99% of this velocity 0.99 u, where we have, that is the boundary of the boundary layer thickness. One boundary at the plate, another boundary is the point where the velocity is equal to the 99% of the free stream velocity. Okay. This is a hypothetical, but it is okay. So, 1% we consider it is okay, no problems. So, that way we consider is a 99% of the velocity, that is what we will define it as the boundary layers upper boundary, and the lower boundary you know it, where you have a velocity is 0, u is equal to 0 value, u equal to the 0 value what you consider it. That is what is 0.99. So, okay, always you can divide it, why not more, but okay. So, it is considered is okay 90%, 99% velocity, the free stream velocity, if it is that is what is defining the upper boundary. The lower boundary anyway this plate. Okay. That is the simplified case, and that is the sigma x is the delta x is the boundary layer thickness, which is varying along the x directions. If you can anticipate it with distance, it will be increasing trend. So, one thing if you look at, as I think it, that the plate thickness can be, length could be a meters, okay, but the boundary layer thickness, again I repeat, very thin in centimeter level or meter levels. So, that centimeter and meter levels, when I look at that, what is the condition? Delta by x will be delta will be much less, the thickness of boundary layers will be much less as compared to the x value, and delta x y value is usually much less than 1 value. So, it is a geometric problem, but that is the thing, that is the reasons again I am highlighting, think it that the conceptually think it that many of the times the boundary layers what you show it, look at this, they write magnified boundary layers, because that they know it, the boundary layers what is there that we cannot show it. Any of the textbook things, that is the reason they write it is a magnified boundary layer with compared to these x dimensions, this is much lesser, and that is the reasons the delta by x is a much lesser than 1 value. That should be the understanding of boundary layers, how does it forms. Okay. That is the reasons if you know it, how we make a smooth profiles of aerofoil wing, or you talk about any high speed cars. Okay, you can see the smooth profiles. That's the reasons that they try to look at the boundary layer thickness formations. That's what they try to look at. That's what is boundary layer is a very thin flow regions where the viscous rotational force are present, and boundary layers are solved with these two boundary conditions. Okay. Outer flow, as I said it is inviscid or the irrotational, we can use the continuity and Euler equations. Bernoulli's equations can give us the pressure field, and we can get the velocity field. That is what we did it. Okay. That is not a so big part. Now, if you look at the basically what we are looking at, if you try to understand it, that as I said it, Today's we have the CFD tools with us. That's not a big issue commercially or freely. Softwares are available to solve these Navier equations. That's not a big issue. It's not now longer to split two domain as boundary layer domains and outer flow regions, okay, or the boundary regions, because CFD can solve it. But as I said it, still we need to have a fluid mechanics knowledge near to the boundary. That's what is done by almost 30 to 40 years with a group of scientists and professors in Europe to solve these problems, and it is really gives a better understanding of the boundary flow, how it happens it, which even if you have the CFD techniques, there are the numerical solutions. There is a issue, but boundary layer can use, which is nothing else, is just a approximations of Navier equations. That's it, again I am telling it, it's nothing else, we are same Navier equations, but it's approximations near to the boundary regions. That's the reasons you have to look it. The boundary thickness distance away from the wall at which the velocity component is parallel to wall, 99% of the velocity speed outside the boundary layers. That the definitions, very simple way I said it. It looks is that if you have a free stream velocity u, you look at the 99% of u, where it is 0.99 of u, that the regions will define as the boundary layers thickness, which is varies with x. In boundary layers, as we have defined the Reynolds flow Reynolds numbers, here also we have define the Reynolds number considering the characteristic length in x direction. That means, what we do it here, Reynolds numbers when we are defining it, this is the x directions, okay. We are defining the flow Reynolds numbers, which is inertia forces by viscous force. That part here characteristic length we have given the x. So, that is what again I could write it, that Rex, the Reynolds numbers what we consider for a boundary layers, okay, as V is free stream velocity, x is characteristic length, from this is the end, from this x value by the mu dynamic viscosity, that is what is we can write B x. So, as the x is increases, the Reynolds numbers is increases, that is what if you look it for a particular free stream velocity V, based on the fluid properties, you know the kinematic viscosity is a constant, but x as it increases, the Reynolds numbers is increases. That will have the same conditions that as we have done for the pipe flow, the flow will go through three phases: laminar, transitional and the turbulent. Here it will depends upon the threshold, the critical Reynolds numbers based on the boundary layers experiment which was done it almost 100 years back, to find out what is the critical Reynolds numbers, to decide which is the regions follows to laminar boundary layers, which is the regions follows to for turbulent boundary layers, or regions in between the transitional boundary layers. So, these the critical Reynolds numbers, which is estimated from the experimental data, conducting plate in a wind tunnels, estimating all these velocity observations, the flow field, they try to find out what is the critical Reynolds numbers to define in the boundary layers itself is the three regions, the laminar, transitional and the turbulent boundary layers. Let me I commit to that figures, which very interestingly if you look at that, if you have a free stream velocity V, and this is the plate as we are considering a symmetric boundary layer conditions, this is the plate and the flow is coming it, as it will be retract it, then flow will be a this is what the sigma x, which is the boundary layer thickness, which is increasing along this, and this is the boundary. Okay, so you can look it as come to the turbulent and all. This will not be smooth, as in a turbulence, as you know it, it will have a lot of verticity will be there, and in transitionals both verticity and decaying of these things will be there. So, which would be so that way in a plate, okay, as we moving with the x directions, there will be regions for laminar boundary layer, transitional boundary layer, and the turbulent boundary layer formed from the experiments. Okay, basically conducts in wind tunnel. A lot of experimental fluid mechanics did it in almost 50 to 80 years. Still we are doing a lot of experimental fluid mechanics. Anyway, here we have not emphasized much. If you look at that from experimental fluid mechanics, they found two critical Reynolds numbers to define flow between laminar transitional and transitional to turbulent. The Reynolds numbers is 1 lakh, okay, it's easy to remember, 1 is to 10 to the power 5. So, in case of Reynolds numbers, if it is lesser than that critical Reynolds number lesser than 1 lakh, 1 is to 10 to the power 5, okay, 1 lakh, 1 is to 10 to the power 5. If a Reynolds number is lesser than this is the critical Reynolds numbers, then flow is laminar, which is easy for us. Okay, we can think it that to get analytical solutions for that. That is what we will discuss. So, if I have a laminar turbulent laminar boundary layers, we can find out these Reynolds numbers, because you know the free stream velocity, you know this x value, you know the fluid kinematic properties. So, viscosity. So, you can find out whether it does it below the this critical numbers, which is 1 lakh, less than 1 lakhs. If it is that, that is a laminar boundary. And another critical limit is that for the turbulent boundary layer, is if the Reynolds numbers is greater than 3 millions, okay, 3 10 to the power 6, just remember it, okay, 3 10 to the power 6, 3 million, this is 1 lakh, this is 3 million. If it is more than that, you will have a turbulent boundary layers, you will have turbulent boundary layers. So, either these turbulent boundary layers we can solve using CFD solvers, or we have to work from experiment. Okay. Here we do not have any analytical solutions for this. So, either you look for CFD or experimental fluid mechanics, okay, fluid test. Okay. Here we in the laminar zones, again I will come to basic equations. Here we can get some sort of analytical solutions. Okay. So, what it happened to these transitional zones, which is in between laminar and turbulent zones? Even in the best CFD softwares today also unable to represent this transitional flow, because when the transitional flow is there, it is more complex flow patterns happens in these regions. Again I am repeating it, it is very complex flow happens as compared to the turbulent. No doubt the laminar flow is easy to understood it, but the transitional is more complex as the generation, growth, decay of all the patterns happens here. So, transitional part is very difficult, even if you today we have a very advanced level of CFD solvers. still we cannot solve this transitional case, and many of the designer case we try to avoid this transitional zone. So, what we do it, but like a in case of aircraft wings things, we try to put it a structures such a way that we should try to avoid these transitional zones, because because of this transitional zone there will be acoustic component, there will be other complex components, heat generation component, all will be the complexity will come it. To avoid that, many of the times we put the rings, okay, some sort of artificial roughness, okay. You put a trip wires, okay. Like if you look at this is the trip wires we put it to reduce the transitional zones, to make it from laminar to turbulent zone. More emphasis I am giving it, please draw the velocity distributions, okay. What will be the velocity distribution for laminar, what will be the turbulent, and since there is a presence of a trip wire, okay, is a artificial resistance we put it, so that it initiate early transitions to the turbulence, okay. That is what we follow it. And this eddies from the trip wires cause enhanced local mixing and create the disturbance that very quickly lead to a turbulent boundary layers. That is what we follow it most of the designing, to try to avoid these transitional zones, because that is the reasons we put the trip wire to facilitate as quickly as possible from laminar to the turbulent zone. Now, if you look at another very interesting part to show you that many of the times we believe it the turbulent the boundary layer formations happens near to the plate, okay. That is what we presented at some of the books, but not necessarily. Boundary layers happens in many places. Let me I show you to that as we have given this that this is the boundary layer, and you have these outer layers and this. And if you look at these two cases of experiment cases, that you have a Reynolds numbers is 10 to the power 2, it is okay, and 10 to the power 4. Okay, so, it is almost 100 times the higher the Reynolds numbers. Okay. Higher the Reynolds numbers we have, either you can increase the velocity, because anyway if you increase the velocity you will have this. So, if you look at as the higher the Reynolds numbers, these are the experimental finding, also analytically also we can get it that trend. As higher the Reynolds numbers, okay, the Reynolds numbers as increase by 100 times, okay, from this figure to this figure, the thickness will going to decrease it. So, higher the Reynolds number, thinner the boundary layers. That is what you have to remember it, or conceptually we try to understand it, that when you have a higher Reynolds numbers, that means the ratio between the inertia viscous force, okay, that is the numbers we are enacting, is that you can understand it, the thickness will reduce it, the viscous force is lesser as compared to the inertia forces. So, that is what experimentally also we can see it, that when you change the Reynolds number, it is almost 100 times, okay, the thickness will be decrease it, and here showing this again I am emphasizing that just look at the velocity distributions, because of the presence of different Reynolds numbers you will give a different velocity distributions profiles, and beyond these outer regions the velocity will be more or less the constants, because it has reached to the 0.99 of u, 90% of the free stream velocity. So, you will not have a much gradient. So, this is the relationship between the Reynolds numbers and the boundary layer thickness. So, higher the Reynolds numbers, thinner the boundary layers. As I said it, that boundary layer formations happens in many places. Like for example, you have a jet, okay. maybe you have a smoke, some jet, chemical jet you are injecting it. Okay, just like two tanks, there is a water jet. So, we have a water jet, this is the fluid, another fluid jet is happening it. So, if you have a water jet is happening, so you can see that the velocity distributions will be like this and velocity distributions will be z. So, if you look at this is the boundary layers. Symmetrically, if I look at this is the boundary layers, even if of case of a jet flow. If I have a two liquids, one is I am having a jet. So, as we this jet will disperse it, that is what is I can see it, that this is and this is what the boundary layer formations. This is the fluid and this is the fluid, fluid may be rest, and this jet part, this is what is showing me the boundary layers. So, and this is the symmetric line for me, this is the symmetric lines and this is the distribution showing me the how the velocity fields are happening. So, you can understand it for the jet problems also we can make it as equivalent flow past a flat plates, or I just showed it. I have the cars. So, top of the cars I can represent a different regions of the boundary layers. I can try to solve it. So, that is the reason the boundary layer the tools to solve many of the problems. It is not the tools as presented in some of the test book, it is just for a flat plate, that is not there. That is what my point, you try to understand the boundary layer concept, and that concept you can, even if you solve the jet problems, you can use the same concept how boundary layers we can form it. Similarly, the wake formations, like a boat is moving it, as you know it, just for your understanding I am putting it to that. A wake formations, a boat is moving with velocity v, then you are having the wake formations. You can see that any ship is moving it, and from the top you can see that wake formations. So, that wake formations also can be considered it, as you see that this is the velocity and this is the 99% velocity points as a constants, then velocity distributions like these, like these. So, this is also can be considered as the boundary layer concept to solve how the wake formations growings are happening it. Just if a boat is moving, the downstream of boat there will be wake formations, and that wake formations you can say as equivalent as similar to the boundary layer formations. That is what the wake formations we can do it. Not only that, if the two velocity fields are mixing it, okay, there is two fields are there, one is moving with v2 velocity, another is v1 velocity, and this is the interface layers. So, if you see that because of these two velocity zones are mixing, v1 and v2 is greater than v1 value. So, you will have these distributions which will be symmetric distribution. This is also the same way what we are talking about the boundary layer passing on a flat plate. So, boundary layer approximation the techniques to solve this approximate the Navier-Stokes equations, not only the flow past a flat plate, also we can solve jets problems, we can solve the wakes problems or mixing layer problems. So, with this let I conclude today lectures, and tomorrow we will talk about how we can derive these boundary layer equations and some of the approximate solutions. Thank you.